Let's take a look at section 7.6, one of my favorite homework sections, I believe, of the entire semester. This is the one where we're trying to combine many different types of integration within the same assignment. Some of the problems, like this first problem assigned, will tell you what to do, and then others, just by looking at the problem, you'll have to understand what best technique of integration should be used to attack the specific problem. So on this first one, we're given the integral of 1 over x squared on the square root of 16 minus x squared integrated with respect to x. They tell you to use trigonometric substitution. You should not have had to have been told that, because as soon as I see that 16 minus x squared in there, I'm thinking, okay, that's a squared minus x squared. Anytime you have a squared minus x squared, you know you could use the trigonometric substitution to let x equal a sine theta. Well, in this case, a squared is 16, so a is 4. I'll let x equal 4 sine theta. Now, derivative of that, dx is going to be 4 cosine of theta d theta. So now that square root of 16 minus x squared becomes the square root of 16 minus 16 sine squared. And then I can say, well, I know I could factor a 16 out on the inside, and then I would have 1 minus sine squared left. Well, 1 minus sine squared is cosine squared. The square root of 16 times cosine squared is going to be 4 cosine theta. Now that I know everything here, I can go back to my problem and substitute in. The dx was my 4 cosine theta d theta. X squared is just going to be 16 sine squared. And then we know that the square root I've shown right here is equal to 4 cosine theta. So now I simplify. Clearly I have a factor of 4 cosine theta in the numerator and denominator. Those eliminate. I factor the 16 out. Since it's in the denominator, it becomes a 1/16 on the outside. And then you'd say, well, the only thing you would have left on the inside is 1 over sine squared d theta. Instead of writing that, I just said, well, I know 1 over sine squared is the same thing as cosecant squared. And then you go back to your Calc 1 knowledge and say, what did I take the derivative of to get a cosecant squared? You say, well, derivative of cotangent is negative cosecant squared. So I know that the integral of a positive cosecant squared would be a negative cotangent. So my answer is going to be negative 1/16 cotangent theta plus c. Now, as soon as you get to this, you can say, okay, we've integrated. The next and final step here is to put this back in terms of x. We do that by drawing our trig triangle. Our trig triangle is established by our trig substitution. X is equal to 4 sine theta. So x over 4 is equal to the sine of theta. Then I know theta is an angle inside of a right triangle that has an opposite side of x and a hypotenuse of 4. So I label those, which means my adjacent side has to be the square root of the hypotenuse squared minus the other leg squared, 16 minus x squared. And remember, the expression from the original problem must always come into your trig triangle. Now, we go over here and say, all right, this is my trig triangle. How is that going to tell me what the cosine of theta is? Well, here's my theta. I know that the tangent is the ratio of opposite over adjacent. Cotangent is adjacent over opposite. So it's the square root of 16 minus x squared over x. I have that multiplied by negative 1/16. So I can say, well, my answer is going to be the negative square root of 16 minus x squared, all divided by 16x, plus that gorgeous constant of integration, final answer. And you'll see that that is precisely how I entered the answer into Achieve here, and it's the answer that they liked. Now, for the next question here, very quick question. It's just second power of a cosine function. I think they'll change your angle is about the only thing that's going to be different from one problem to another. So you'll see here, all I've done is I've used my power reduction formula. I need you to remember the power reduction for cosine squared of any angle. It's 1/2 times the group, 1 plus the cosine of twice the angle. It's precisely what I did here. Cosine squared of 9x is equal to 1/2 times the group, 1 plus the cosine of twice the angle. Well, the angle was 9x. Now it's 18x. Now I have to integrate this group, and I do need that as a group in there. And I can say, well, the integral of the first term in that group with respect to x is just going to be x. Still have my 1/2 on the outside. The integral of the cosine of 18x, I can say, well, that's going to be the sine of 18x divided by the derivative of the angle 18. All of this plus your constant of integration. The only thing I've done after that is I distributed, through the 1/2 to get 1/2 x plus 1/36 sine of 18x plus your constant of integration. Nice final answer there. And you can see that, again, that's the exact same way I entered it on Achieve. For the next question here, it gave me the integral of 1/49 plus x squared quantity squared. Now, this problem took a little bit more space, so let me go ahead and maximize this screen. Here's where I worked out number 3. Have the integral of dx over 49 plus x squared quantity squared. As soon as I saw that a squared plus x squared, I'm thinking, well, this is trig substitution again. I know I'm going to let x equal a tangent theta, which in this case is going to be 7 tangent theta. So dx, the derivative of that, derivative of tangent is secant squared. I'll get 7 secant squared theta d theta. That group, 49 plus x squared quantity squared. We can say, well, that's going to be 49 plus 49 tangent squared theta. We're squaring that group. On the inside of that group, this would simplify to be 49 times 1 plus tangent squared. We know 1 plus tangent squared is secant squared, so we'd have 49 secant squared theta squared. Well, 49 squared is where I got the 2,401 from, and of course secant squared is secant to the 4th. So that denominator here is going to simplify to this. I'm trying to show what everything simplifies in the integral before substituting it in. So this is where everything's coming from. That denominator, the 2401 secant to the 4th theta. The numerator is just dx, which we know is our 7 secant squared theta d theta. So now I go in here and I can say, well, all right, this 7 over 2,401 is going to reduce down as 1/343. And then I can say, well, after I do that, I would just have a secant squared left in the denominator. Well, if I have a secant squared left in the denominator, that's the same thing as a cosine squared in the numerator. Now that I know I have a cosine squared in that numerator, it's very similar to the one preceding it. I can just say, well, I'll use the power reduction formula and say this is going to equal 1/2 times 1 plus the cosine of twice that angle. So the 1/2 came out, multiplied the 1/343 to get 1/686. And then I have 1 plus the cosine of twice that angle theta. Now, when I integrate this, of course, no big deal. That's where this came from. I can say this integral is going to equal 1/686. The integral of 1 with respect to theta is theta. The integral of the cosine of 2 theta is the sine of 2 theta over 2. Now, unlike the preceding problem, you could just leave that in there because I never had to use a trig substitution to work backwards to the original value. I kept it in terms of x. I can't leave that double angle in this problem if I hope to get back in terms of x, so now I have to use another trig identity, the double angle formula for the sine function. The sine of 2 theta is 2 sine theta cosine theta. So now, when I try to go to my next step and put things in terms of x, I already know in order to go from this step to this step, I need to be thinking of my trig triangle. Trig triangle comes from your trig substitution. You can say, well, I know that x divided by 7 is the tangent of theta. Use that to construct your trig triangle. Theta is the angle inside of a right triangle whose opposite side is x and adjacent side is 7. So I get x and 7, which means the hypotenuse has to be the square root of this side squared plus this side squared, and it gives you the expression from the original problem back, which is always a great thing. Now, I go in here and I can say, well, what's theta in this case? Please notice, tangent of theta is x over 7, so if you solve for theta, You can say, well, theta is equal to the inverse tangent of x over 7. That's where this came from. Now, the second term in here, I keep in mind this 2 and this 2 in the denominator are just going to cancel. So that second term is nothing more than sine theta cosine theta. That's what this and this is. The first term, sine theta, opposite over hypotenuse. Second term times cosine theta, adjacent over hypotenuse. So that's just sine cosine there, plus c. Now, the only thing I've done to simplify, distribute through your 1 over 686. You get 1 over 686 inverse tangent of x over 7. And then in that second term, the 7 over 686 reduced down to 1 over 98. That just left me a numerator of x and a denominator of 98 times the group. And since you have a square root times a square root, you're going to have that group 49 plus x squared. And now it's going to be raised to the first power, since you have a square root times a square root. And we know that that's just going to be the group to the first, plus your constant of integration. It's a nice final answer there. And let me see, that's a little bit blurry there. I'll see if I can fix it. There, that's better. Now, keep in mind that this is the same way I entered my answer into Achieve, and Achieve liked it. That was not always the case with the way I wanted to input answers in this section. I'll talk about some input problems and some later problems in this assignment. For number 4 here, we have the integral of tangent to the 5th of 10x times the secant of 10x. Instantly, what you're supposed to be thinking of in this problem is you say, well, okay, I know if I have an odd power of sine, cosine, tangent, or cotangent, I'm supposed to work with that. You only work with secant or cosecant if you have an even power. So clearly, tangent to the 5th power, that's what you want to manipulate. How do you manipulate it? You rewrite all of the tangent function in terms of secant, except for one power of the tangent. So I can say, okay, then this is tangent to the 4th times tangent to the 1st. Tangent squared is the same thing as secant squared minus 1. So since that's the same thing as tangent squared, tangent to the 4th is just tangent squared squared. So all of this is replacing 4 powers of the tangent, and then there's my 5th power of the tangent. I pull that into my problem. I'll say, well, I'm going to put that secant squared of 10x minus 1 quantity squared out in the beginning. Then I'll have my secant of 10x times the remaining factor of the tangent of 10x, and I'm still integrating with respect to x, of course. Here I can say, well, now let's do the u substitution. If I let u equal the secant of 10x, derivative of secant is secant tangent, so the derivative of the secant of 10x is 10 secant of 10x tangent of 10x dx. I didn't see the 10 on the inside, so clearly I multiplied by 10 on the inside, and it got changed to du in the next step. But if I do that, I need to divide by 10 on the outside. That's where this came from. The 10 secant x tangent x dx all became du. I have 1 over 10 on the integral. This just becomes the group u squared minus 1 quantity squared. Now please be careful with that. You can't do the integral or the calculus integration here until you take care of the algebra in this problem. So you need to multiply u squared minus 1 times itself. And when you do, the inside is going to be u to the 4th minus 2u squared plus 1. At that point, it's just your power rule integral. You'll have u to the 5th over 5 minus 2u cubed over 3 plus u. Don't forget your factor of 1 over 10 out in front, plus your constant integration. Then I just said, well, now my first term is going to have a coefficient of 1 over 50, and u to the 5th becomes the secant to the 5th of 10x. And then I would have minus 2 over 30, which reduces down to 1 over 15, secant cubed of 10x. And then I would have 1 over 10. I almost forgot to put the 1 over 10. I had to scrunch it in there. Plus 1 over 10 times u, which becomes the secant of 10x, plus the constant of integration. And you can see that that's exactly how I entered it in to Achieve, and Achieve liked it again. Now the next question here, before you work this question, you should have instantly known what to do in this one. As soon as you see the natural log in there, that's a strong indicator that automatically you're going to be using integration by parts. Now this is actually a beautiful problem though, because even after you do integration by parts, you're not done. So let's talk about the most efficient way to work this problem. It is certainly to use integration by parts in your first step. So I set the natural log of x to the fourth minus 81 equal to u. Then du, derivative of any logarithmic function, is the derivative of what's inside the logarithm divided by what's inside the logarithm. So it's always 1 over x times dx. And you say, well, the derivative of the inside gave me 4x cubed over what was inside, taking the derivative with respect to x. Now, the dv in this problem just becomes the 1 dx, and the integral of 1 with respect to x takes me backwards to x to the first power. Now, integration by parts formula, u times v, that's where this right here comes from, minus the integral of v du. Well, v times du, that's going to give me x times 4x cubed for 4x to the fourth over that denominator. And then as soon as I saw that I have an integral with a fraction or a rational function, and I know that the degree of the numerator and denominator is the same, I knew instantly I'm supposed to use long division to simplify that out. That's what I showed over here. If I divide that denominator into the numerator here, then I know x to the fourth goes into 4x to the fourth 4 times. I'll get my 4x to the fourth. 4 times negative 81 gave me minus 324. Please be careful, you've got to subtract that whole group. The 4x to the fourth cancel, just as it should, but then you'll have a plus 324 left over. Now I can say, and I might have, oh no, I started to say I had a wrong sign, but no, it's minus because of the sign out in front. Everything's fine. So now I go back to my formula, and I can say, well, I know that my integral solution is equal to this original u times v, yes, minus whatever I get for the inside of this integral. Well, that's going to become minus the part that divided out evenly is just going to be the integral of 4 with respect to x. And now remember, this remainder means it's still divided by what's inside. So I can say, well, all right, why is it minus? Because this entire integral was being subtracted. So you say minus, and I'll factor the 324 out, and I'll have the integral of, if I factor the 324 out, my numerator is now just a 1. That denominator, instead of writing as x to the fourth minus 81, I went ahead and did what I knew I would have to do. Couldn't leave that denominator as x to the fourth minus 81. I recognized it as a difference of 2 squares. It factored to be x squared plus 9 times x squared minus 9. And then x squared minus 9 further factors to its linear factors of x plus 3 times x minus 3. Now, I already know that's going to be not complicated, but it's going to be quite a bit more work to do. So I went ahead and showed that right here. This one and this, well, this one's already done. This one's very easily done. It's just going to be 4x. This one's going to take some more work. I show that work right here. So I take the fraction on the inside and I can say, well, I know that for every irreducible quadratic factor, it's going to have a separate linear numerator. So I have ax plus b over x squared plus 9 plus c over x plus 3 plus d over x minus 3. Now, what I did in this step is I went ahead and multiplied the entire equation by that least common denominator. And when I do that, of course, the left-hand side is just the numerator of 1. When I do that to the right-hand side, ax plus b is going to end up multiplying these other two denominators, the x plus 3 and x minus 3. The c is going to multiply x plus 9 and x minus 3. And the d is going to multiply these two, the x squared plus 9 and the x plus 3. Okay, now, in order to try to solve out something, I'm looking at this and saying, oh, I think I can solve for c if I let x equal negative 3. I do that. If I allow x to equal negative 3 inside this equation, I know the left-hand side, it's still a 1. so I keep the 1 over there. On the right-hand side, why does the a and b cancel out? Because if you let x equal -3, they're multiplied by a factor of 0. Same thing's true for d. It'd be multiplied by a factor of 0. C would be multiplied by -3 squared, which is 9. 9 plus 9 is 18, and a factor of -6. Well, -6 times 18 is a -108. So -108c is equal to 1. Thus, I can see that the answer is -1/108. Now, similarly, I can solve for d if I allow x to equal 3. Left-hand side is 1. The right-hand side, all of these terms will cancel, and you'll have d times 18 times 6. Again, very similar to the last case, you're going to have positive 108d is equal to 1. Thus, d is positive 1/108. Now, those two are the only ones we can get by just plugging in values for x. But I can solve for the other variables too, or the other letters, I should say too. What if I look at the coefficients of the x cubed in this equation? If you look on the left-hand side, you'd say there isn't an x cubed term. It's just a constant of 1. Right. So I can say the coefficient of x cubed on the left is 0. How could you get coefficients of x cubed on the right? I know that a is going to be a coefficient of x cubed. You would have ax times x times x. I know c is going to be a coefficient of x cubed, and keep in mind b is not going to equal a coefficient of x cubed. D would be a coefficient of x cubed. You have dx squared times x for dx cubed. So I know that the coefficients of x cubed on the right would be a plus c plus d. We already know that c and d are just the opposites of one another. So you have a minus 101/108 plus 1/108. That just gives me a plus 0 is equal to 0, which leads me to know a is also equal to 0. So then if I want to solve for the remaining letter, in this case b, I look at the constants in the problem. And it's extremely important for you to understand a can never be the coefficient of a constant because it's tied with the term of x there. Well, clearly the constant on the left-hand side is 1. Well, now, what is the constant that b is going to be a part of? Well, it would be b times 3 times -3. So I would have a -9b that's not going to have any variable x tied with it. That's going to be whatever the constant is. -9b is a constant. Over here, I would have c times 9 times -3. That's -27c is a constant. And then you have plus 9 times 3 times d plus 27d is a constant. Now it's a matter of trying to solve for b. I'll say 1 is equal to -9b. And then I'll have minus 27c. Well, that's going to give me plus 27/108. Plus 27d, it's another plus 27/108. Of course, 27/108 would reduce down to 1/4. So you have -9b plus 1/2 is equal to 1. This allows me to see -9b is equal to a positive 1/2. Therefore, if I divide by -9 on each side, I'll get b is equal to -1/18. Now I go back into my problem and I can say, all right, I'm going back up here and saying this original integral is equal to the x, the original u times v, x natural log of x to the 4th minus 81. This came out to just be minus 4x. Now I have the last group where I've done work, minus 324 times the group. All right, what's the first term inside the group? It's going to be the integral of this fraction. I already know that the a term is 0, and I know that the b is -1/18. So notice I just factored that -1/18 out in front, and then you're going to have a constant of 1 on the inside over x squared plus 9. The next term, you're going to have the integral of this fraction. So I can say, well, all right, c was a -1/108. I'll factor that to the outside times the integral of dx over x plus 3. My last one, inside of this integral, I would have d over x minus 3. d is 1/108. I go ahead and factor that out. And then I'll have 1 over x minus 3 with respect to x. Okay. Now, I know that the last two are easy because the derivative of the denominator is in the numerator. They're just going to be natural log of the absolute value of the denominator. This one's a little bit more complicated, but hopefully by now we've seen this a few times. You're thinking that's not complicated at all. That's easy. I'll show you here on our integration table. It's just number 16 there. Please notice, and I'll make it a little bit larger. It's this one right here, where we say the integral of 1 over a squared plus u squared is 1 over a inverse tangent of u over a plus c. That's precisely what I'm doing in this problem now. I can say, well, all right, for this one, the first two are already done. The next one I had minus 324 times a negative 1 over 18. That gave me a positive. And then I believe 324 divided by 18 gave me an 18. Well, where did the 6 come from? Because I also had to divide by the square root of 9 out front, which divided by an additional factor of 3. 18 over 3 gave me a 6 there. And then I can say, well, that takes care of the coefficient in front side of the inverse tangent, and then it's the inverse tangent of the square root of this number divided by the square root of this number. So x over 3 and the inside of the inverse tangent. Again, that's just following formula number 16 on your table. The last one here, I can say, well, 324 divided by 108, that's going to go 3 times. A negative divided by a negative is going to be a positive. I'll get plus 3. Now, this one would be a positive 3 natural log, the absolute value of x minus 3. I can see my next term would be a minus 3. Well, I just went ahead and combined them to the exact same logarithm and said, let's say that that's plus 3 natural log of the positive term divided by the negative term, x plus 3 over x minus 3. Could have you kept them as 2 separate logs? Of course, it'd have been fine, but I think this is the superior format answer. So now you'll notice on achieve for number 5, that's precisely the way I entered it in with a condensed logarithm, and achieve did like the format of that answer. Going on to the next one. And this is where I thought the problems really started getting fun. The techniques I used in number 6, or was going to use in number 6 initially, were not the greatest idea. Now, first of all, as soon as you see the integral of x squared dx over x squared minus 81 to the 3 over 2 power, I see x squared minus a squared, where a is 9 in that denominator. That's x squared minus 9 squared. Anytime you see x squared minus a squared, you should be thinking the trigonometric substitution to let x equal a secant theta should help. Well, it's a is 9 in this case, so x is equal to 9 secant theta. Well, dx is the derivative of that, 9 secant theta tangent theta, d theta. So then that group x squared minus 81 to the 3 over 2 power, that's going to become 81 secant squared theta minus 81 to the 3 over 2. Well, the inside would factor to be 81 times secant squared theta minus 1. You know, secant squared theta minus 1 is tangent squared. So the inside is 81 tangent squared theta. 81 to the 3 over 2 power means the square root of 81, which is 9, and then raise that to the 3rd power. 9 times 9 times 9, 729. Same thing with the tangent squared. You'd say, well, the square root of tangent squared is tangent. Now you got to raise that to the 3rd power to get tangent cubed. So that entire denominator is going to simplify to be 729 tangent cubed theta. The numerator, I had x squared. Well, x squared is going to become 81 secant squared theta. That's where this came from. Times dx. Well, dx is my 9 secant theta tangent theta, d theta. Now I quickly saw that 9 times 81 is 729. That's just going to cancel with the 729 in your denominator. 1 power of tangent is going to cancel with the denominator to leave you tangent squared in the denominator. But my numerator would be secant cubed. Now, what I initially thought to do in this problem, and you'll see I went ahead and started doing it, is I said, well, I'm going to let secant cubed be 1 over cosine cubed. And then I know I'm dividing that by sine squared over cosine squared. If you divide by sine squared over cosine squared, you multiply by cosine squared over sine squared. Now, how did I immediately, as soon as I do this, realize it's not helpful? Well, I was just looking at it and saying, well, I'm not going to have anything left in the numerator. I'm going to have a 1, and then I'm going to have a cosine theta, sine squared theta in that denominator. I can't do a substitution when both terms in the problem are in the denominator. So I automatically knew, okay, I'm not going to try that and try something else. So this is going back to the drawing board over here, here to here. From in this step, I said, okay, secant cubed theta, I'm supposed to remember that I know that secant squared theta is equal to 1 plus tangent squared. So secant cubed can be secant squared times secant. For secant squared, I can call 1 plus tangent squared times the remaining factor of secant, all divided by my denominator tangent squared. So I'm thinking, okay, maybe this will help. Well, here's what I've done. From this step to this step is I've distributed that secant throughout each term in this first group, 1 plus tangent squared, and then I've separated it over that denominator of tangent squared. So I would get secant over tangent squared. My second term would be tangent squared secant over tangent squared, and in that term the tangent squared would cancel and you just have your secant of theta. Now, I already know that the integral, and I have it memorized, I hope you do too, the integral of the secant theta d theta is the natural log of secant theta plus tangent theta plus c. That's just your table number 13 formula to go from here to here. But now, that first one, still problematic. So I went back and tried the same thing I was going to do up here. Now it's different. So you can say, I bet that will help. Now, the secant is 1 over cosine, dividing by tangent squared, which means you're going to be multiplying by cosine squared over sine squared. Now it sure is different because there's a cosine factor left in the numerator over a sine squared. So again, this second part, I just went ahead and integrated the second integral. That's table 13 or from memory. So I can say, all right, this first integral is going to simplify down to this. The second integral, I've already integrated. And I don't put the plus c just yet because the c could be absorbed by this first integral. So now I can say, well, how do I simplify that first integral once I cancel out the cosine in the denominator? I use substitution. Let u equal the sine of theta, d use the cosine theta d theta. And then you can say, okay, then all of that goes away. You're just going to have 1 over sine squared, which becomes 1 over u squared du. 1 over u squared du is u to the negative 2 du. And I've went ahead and showed the thought here. If you integrate u to the negative 2, it becomes u to the negative 1 over negative 1. You say, well, that's the same thing as negative 1 over u to the first plus c. So now I can say, well, all of this is going to simplify to be negative 1 over u, where u is the sine of theta, plus the natural log of the secant theta plus tangent theta. And now that I'm done with all of the integration, I do need to put plus the constant of integration. Now, I've had my answer in terms of theta. I need my answer in terms of x. So I refer back up to my trig triangle up here. It was initiated by your trig substitution. You can say, well, we know that x over 9 is equal to the secant of theta. Remember, secant's the reciprocal of cosine. Cosine would be adjacent over hypotenuse. So this is the ratio of hypotenuse over adjacent. So I go ahead and I can say I can label this as x. This, the adjacent, is 9, which means the side opposite has to be the square root of x squared minus 9 squared, or x squared minus 81. And again, that expression must pop up in your trig triangle, and it does. So now I go back to my problem, and I can say, well, your first part is negative 1 over the sine of theta. So I can look up here and say, well, I know that the sine of theta would be opposite over hypotenuse. 1 over the sine of theta is the reciprocal of that, so it's going to be hypotenuse over opposite. And I can say, well, that's going to be x over the root, and then it's negative. That's where the negative x over that root came from. Then plus the natural log. And when I'm thinking about the secant function and the tangent function, I know that they both have a denominator of 9. So instead of putting them as separate fractions, x over 9 plus the square root of x squared minus 81 over 9, just went ahead and said it's x plus the square root of x squared minus 81, both divided by 9. They had a common denominator, plus your constant of integration. Now, if you put this answer on Achieve, it's going to count it wrong. Why? This is where they say make sure as much of the constant gets absorbed by C as possible. They do not want that division of 9 inside the natural log. I tried to explain it in the next step by saying, well, okay, this term's fine. Your natural log, anytime you have a numerator and a denominator, if one of those is just a constant, then you don't want it in there, because I can say I could separate that up and it'd be the natural log of this function of x minus the natural log of 9. But the natural log of 9 is just a constant, so this is where we say it gets absorbed, as they're talking about on Achieve, by the constant of integration. This goes together and just becomes c, and you just have your first two terms there plus c. Final answer there. And that is a gorgeous problem. Loved that one. And you'll see that exactly how I mentioned, they do want the absolute value of the x plus the square root of x squared minus 81, all inside the absolute value plus c. And as a side note, please remember when you put these natural log answers that you remember to put the absolute value in those. Otherwise, it's going to not count your answer correct. I've had some trouble with those a few times. Even though I put it on my paper, I forget to put it in to Achieve. All right, so I'll look at the remainder of the problems in another video. Hopefully this gets you well on a good start for this section. There are some absolutely wonderful problems in this section.